Hello, it's Keith here, and this is lesson 48 of the platform-specific series of my 6502 assembly programming tutorials, and I have an oscilloscope above me, and that's because we're looking at sound on the PC Engine. Now, we've done sound once before. I wrote a little driver called ChibiSound, which was a simple bleeps and bloops sound effects driver for simple Atari-style games that just needed the odd bleep to make the game not silent. Now, this wasn't really enough for anything particularly advanced, like music, but it was enough for the simple games I was working on at the time. But time's passed on now, and I'm no longer satisfied with that. I've used Arcus Tracker in the past for my music, but that's a Z80 based sound piece of software. It's great, but it's only Z80 based, and porting to other systems is a bit difficult. So what I'm doing is I'm writing my own sound software. I'm writing a program called Chibi Tracker Pro. I've got a sound player called Chibi Tracks, and these work by linking to an underlying sound driver known as the ChibiSound Pro driver. This allows for more complex sound on multiple channels. Now, I should point out that the Pro suffix is a bit of a joke. It's based on Sound Blaster Pro, which wasn't particularly amazing. It was better than what came before, but far inferior to the Sound Blaster 16 and the following ones. Anyway, so we're going to be creating this driver today, and it basically allows us some extensions on what the last one did. Now, the last one only allowed for a high and low volume. It's only allowed for noise to be on and off, and it's only allowed for 63 different pitches. Now, it also only allowed for only one channel, which wasn't really up to very much. The new version allows for noise to be on and off. It allows for up to 127 channels, in theory at least, volumes of 0 to 255, and pitches from 0 to 65535. Now, the pitches, the low pitch will be the same 0 on all systems, and the high pitch will be a high number on all systems. However, the pitches aren't matched across systems, so the PC Engine, the pitch 32768 won't be the same as on the NES, for example. But what we have is we have a lookup table which matches these to the notes of the octave, and this allows us, hopefully, to be able to play a music file and for it to sound something like the same music on each system. Obviously, there'll be limitations. Now, one of these limitations is we're not supporting advanced functionality of the systems. So, for example, things like envelopes for the systems that have it, we don't support those. We would have to simulate them by manually changing the volume or the pitch across time, because that's hard to port to all of these different systems, so we don't try to. Anyway, when we're using this piece of software, the way we use it is it's based on the Z80, so we're using 0-page entries that are marked, and we'll just turn off the oscilloscope for a second. H, L, and DE. Now, DE is the pitch, that's a 16-bit value. L is the volume, that's an 8-bit value, and H is doing two things. Now, bits 0 to 6 are the channel number, so that is 0 to 127, and bit 7 is the noise on and off, and that's the only option we have, the noise on and off. We don't have any more advanced functionality. So still relatively limited, but as I say, now we've got enough to do music, whereas before we didn't. Now, the PC Engine version, we are going to be controlling the PC Engine sound hardware, and this uses ports 800 onwards, so memory mapped ports. We have a channel select. We have a main amplitude, which is kind of the mixer level for all of the channels, and then we have the other ones that are set for specific channels. Now, on the PC Engine, channels 4 and 5 are noise channels, and 0 to 5 are sort of general tone channels. Now, in theory, we could be past a channel number of 0 to 127, but actually, for the ChibiSound software, the Chibi Tracker software, we're currently only really using 3 channels like the AY did. So we're actually going to only configure this to work with 4 tone channels, and we're going to redirect any of the noise options to channel 4. So we're going to only use 1 noise channel and 4 tone channels, and that will be enough for what we require. Okay, well, enough talk now. Let's actually go over to the other screen and let's hear some sounds from the ChibiSound software. Okay, so we've got this test program here. This is what I use to check the pitches and also the noise function. So if I just fire this up here, so you can hear we've got a tone here and we've got a number on the screen. And if I use my joystick buttons here, the keyboard, you can see I can set the various pitches. And if I press the fire button, where is it? There we go. So we can toggle the noise on and off as well. So this is just a little program that I've been using to test the functionality and to get the pitches right for the octave table, because we need that octave table for this. This is the Chibi Tracker. This is the Chibi Tracks software. And this is playing the music from the Suck Hunt game. This was actually written originally with Arcus Tracker, but I've converted it. I've got a converter to convert the patterns, and then I've recreated the instruments so you can hear the music here. So this is just an example here, just to show that what we're doing today does allow us to play music, and it does it in a multi-platform way, because as I say, this song wasn't even composed for Chibi Tracker, it was composed for Arcus Tracker, but we have enough functionality to recreate similar sounding instruments, and we can make music that will work on multiple sounds, multiple CPUs, multiple different pieces of underlying sound hardware because of this ChibiSound Pro driver. So what we're going to do today is we're going to look at the ChibiSound driver, and the first thing the ChibiSound driver has, let's just turn that off, is we have the Chibi Octave. Now this is a lookup table of 16-bit values for various notes in the octave, and these are the pure tones. If we want to sharpen a flat, we can just add 2 together and divide it by 2, and that will give us the value in between. You can see we have various octaves here. Octave 1 to 6 are the main defined ones. 0 does anything lower than the first octave, so we just span out the remainder of the range. And 7 is the highest, which again spans out the highest values. So we sort of have 8 in total, but only 6 are pitch matched. So there we go. So that's what we've got for the octave, and that's what allows us to play notes that match as we would want for our music. When it comes to the ChibiSound Pro driver, we do need a few pieces of memory though. Now we've got this variable defined ChibiSound RAM, which is for the Chibi Tracker software, and anything over byte 64 is spare, and we're going to use 4 bytes for channel noise flags. Now you see the way the ChibiSound Pro driver works is it requires all of the channels to be able to support noise. However, we're redirecting all of the channels to channel 4, and we're playing all of the noise on that one channel, and so when we're told to turn the sound on or off by the calling software, we're going to monitor the virtual channel and say, well, was the noise previously on, was it off? And if it was on before, we're going to turn channel 4's sound off so that the noise is off now. That's how we're going to deal with it. So there we go. So that's what we're doing. Now, before we can actually do anything, we need to do a little bit of initialization, and we need to get the hardware set up so we can make any sounds at all. So the first thing we're doing is we're using port 801, and we're setting the volume to maximum. Now this is the sort of global level. It affects all of the channels, and we're setting the left and the right to maximum here using that there. So that's what we're doing here. And then what we're going to do is we're going to initialize all 6 channels. Now you see the PC Engine uses a sort of wavetable synthesis. Basically we need a wave sample to make any kind of sound at all, and so we're going to have to define these 5-bit samples that make up the wave. Now there's 32 in total, and what we're going to do is we're going to define 16 of them to be high and 16 of them to be low, and this is going to form a square wave. Just before we do that though, what we've got to do first is we've got to select the sound channel. We're starting from channel 5 and we're going down to 0 here. And then what we need to do is we need to select the channel with port 800 channel select. So that's what we're doing here. We're storing X to channel 800, which selects the channel. Then what we're doing is we are setting the left and the right volume of the channel. Now the ChibiSound Pro driver doesn't support setting channel positions at this stage, because that isn't something that a lot of systems support. We're generally only supporting the minimal set of functionality. So we can set the volume level, but we can't set the panning position. So what we're doing here is we're setting the panning position to center here. Now what we're doing next is we are writing a byte to port 8004, which is the channel on or off, and we're basically setting the channel off, and we're setting it to 0 volume as well. That's the sort of mono volume, if we will. So we're turning the channel off here, and then what we're going to do is we're going to do 2 bytes of 16 bytes, and we're going to write first the value here, which is all of the bits to on, and we're going to write basically 16 bytes of that value to port 806, which is the waveform data here. So this is defining the wave sound file that we're going to basically play when this channel plays, and as we change the pitch, that wave will be altered by the hardware to make the pitch higher and lower. So we're writing the first 16 bytes with this value set to 1. We're then flipping all those bits from 1 to 0, and we're writing them set to 0. And so that has built up our wave file. Now once we've done a single channel, we're decreasing X. Now we want to run this when X goes to 0, but we want to then give up when X goes below 0. So we're using branch if plus, because if the top bit has gone to a 1 and we've gone below 0, then we want to give up, but otherwise we want to continue. So this has basically set up all our sound channels with a valid wave file, with a valid volume level, setting the left and right, but setting the channel to disabled. We're now good to go. So we only need to run this once at the start of our program. when we want to actually set a channel, we use ChibiSound Pro Set here, and this will actually set up one of the channels with a new set of parameters, and we can set the parameters here, as I say, with the 0 page entries HL and the DE pair. Now we check the L value and we look at the bottom 2 bits because we're effectively going to only support a maximum of 4 tone channels, and this, as I say, is because of the way we're working with the noise channels. So we're taking the bottom 2 bits of L and we're going to then transfer that to Y. So if we specified a higher number, we would basically wrap around, and the way I've defined how ChibiSound Pro should work, we're required to support a maximum of 3 channels, and anything, if we don't have enough channels, we should just prioritize the lower numbers first, and the higher numbers we can do whatever really we want with. So it's perfectly fine to do that because, as I say, the music software I'm really only using 3 channels for anyway. Now once we've got Y set up correctly, we're then testing the top bit of L, which is the noise bit, and if this is 0, we're going to go to not noise, but if it's 1, then we're going to set the noise up for this channel. So the first thing we're doing is we're silencing the previous tone channel because that might have been playing something in the past, and we're now going to redirect the settings of this to channel 4, the noise channel. So we're storing the Y register to port 800, which is the channel select. So we're selecting the channel, and then we're storing a 0 to 804. And 804 is the channel on and volume level, so that will turn the channel off. So we've silenced the tone channel now. So what we're doing next is we're storing a non-zero value to the channel noise parameter for this channel. There's 1 byte per channel, and 0 means the channel is currently set to off for noise, and anything else is set to 1. So our accumulator currently contains the top bit as 1, so that's non-zero, that's fine. So we're storing that flag there, and that's to tell us next time if the channel noise is turned off that it was previously on and we need to switch it off. Now what we're doing is we're switching our channel number to channel 4 because the noise enable only works on channels 4 and 5, so we're going to use that channel instead. Okay. Now at this point, if the noise was off, what we're going to do is we're going to check the previous state of the noise on the virtual sound channel, because remember we would have redirected that to channel 4. Now if it was 0, then that's fine, but if it's not 0, then the noise was previously turned on channel 4 and we need to now turn it off. So what we're doing is we're selecting channel 4 by sending 4 to port 800, and then we are turning the channel noise flag to a 0, turning it off so we don't try and do this next time. And then we're storing a 0 to the channel on flag and the enable noise flag, and 807 is the noise settings. You can see here, noise enable. We're just turning that off as well. I guess we kind of don't need to do that because we're always using this channel for noise anyway, and we've already turned it off with this option here at 804, but for completeness it seemed sensible, so we're turning it off there. Now when we get to this point though, what we're going to do now is we're going to set up the other settings for the channel, the frequency and the volume. So we're storing the channel number from Y into port 800, which of course, as I said before, is the channel select. We're then going to take the H register, which is the volume. Now we have been passed 8 bits of volume, but we need to get rid of a couple of those. So what we're doing here is we're shifting to the right twice, removing 2 of the bits. We're then checking if the remainder is 0, because if it's 0, then we actually want to mute the channel. So in this case, we want to set the top bit to 0, but otherwise we want to set the top bit to 1, and we're doing that with a set carry here and then rotating that in. Why? Well, because the top bit is the enable bit, and so we need to enable that if we want this channel to make any sound. So we're doing that here. Now, once we've done that, we've now got our volume bits in the bottom part of the value, and our enable bit, the E there, set to 1 or 0, depending on if we want this channel on, and we store this to port 804. 804 is the one you just saw. It's the channel on right, and we're setting the bits there. So that has set the volume. Okay. Now what we want to do is we want to set the frequency. Now our frequency is defined by 2 registers. Now the H part is the 4 bits in port 803, and the L part is the 8 bits in 802. Now we've actually got a total of 16 bits that we're being passed, so we're going to have to ditch 4 of those bits. So what we're doing here is we're actually going to do a bit of shifting, and so we're going to shift the D register into the accumulator, and we're going to shift into the E register here. So we're shifting the bits into the accumulator here and into the E register. So basically we're ditching the bottom 4 bits of E here and shifting 4 of the bits from D into E. We're then flipping the bits that we have got in the accumulator because the frequencies actually work in the opposite way to the way that I wanted them to. So we're flipping the bits there of the H byte and we're storing that into 803. We're then loading in the L byte, flipping the bits and storing that into 802, and that is setting up the frequency. We've also set the volume, we've turned the channel on, and we've dealt with the noise. So that is everything done, and so now finally we return. The last thing we've got here is this ChibiSound Pro update function here, and this is for systems like the Spectrum which don't make a constant tone, so we would need to fire some kind of event to keep the tone playing. Not needed for this system, so we just have that pointing to a return command so that it doesn't do anything. And there we go. So that is everything for this system. So we now have our software so that we can make some better sounds and maybe a little bit of music. So if you've liked what you've seen, please go to the website and download this example. If you want something a little bit simpler, then please go and take a look at my original ChibiSound example, which was just for simple beeps, much simpler. If you've liked this and if you're interested in this idea of me writing my own music software, please consider backing me on Patreon, because it's taking an inordinate amount of time to write music software, and I don't get paid for anything for it otherwise, and I really can't justify keeping doing it, unfortunately, because there's so many other things that are taking up my time. So anyway, just something to think about. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.